11. Recessive inherited disease only showing up in type O blood people, even though type O blood is inherited independent of this disease. So you got a normal man with type A blood and a normal woman with type B blood. You have one child with the disease. So that tells me that one parent is heterozygous for A, the other parent is heterozygous for B, and they have a child with the disease, right? So they have to be heterozygous because if you have the disease, you have to have type O blood. So their child has to have type O blood. And the parents are carriers. So for this disease, let's use D for disease. They're carriers. It's a recessive disease. The woman's now pregnant for the second time. What's the probability that the second child will also have the disease? Assume they're heterozygous for the disease. Yes, I did. Okay, so they have to have a child who's little I, little d, basically. That's what the question is asking. Like if the child is AI, little d, they don't have the disease because you have to have type O blood to have the disease or to show the disease. All right, so the probability of type O blood is 1/4, right? You should be able to run a Punnett square to show that at this point. The probability of being homozygous recessive if both parents are carriers is also 1/4. So the probability of both of these happening, O and disease, is 1/16. All right, a recessive allele causes an absence of fur pigmentation, white tiger, and cross-eyed. If two phenotypically normal tigers that are heterozygous at this locus are mated, so locus is just the location. So at those locations, they're heterozygous. What percentage of their offspring will be cross-eyed? What percentage will be white? One-fourth will be cross-eyed. 1/4 will be white, because if you are white, you are also cross-eyed. So like there's like you don't do a fourth times a fourth, because they're not independent. If you're one, you're also the other. So it's just 1/4. Okay, that's number 12. Number 13. Okay, if this equals no color. If you have this allele, you do not have color. If you're little I, you can have color. But then there's another gene that determines what the actual color is. So big P equals purple, and little p equals red. This is basically a dihybrid cross. It's just the phenotypes get weird because you have to consider what they are for I. So you're doing big P, little p, that's purple, times big P, little p, that's purple, but the parents don't actually have a color because they're heterozygous for I. Right, so the corn looks like white corn, even though they have the genetics to make purple and red babies. All right, so this is very similar to problem number 1 with like pink flowers, right? It's a very similar concept. So let's do, a Punnett square for P. You can have red. I'm sorry, this would be purple. Big P is purple. Purple, heterozygous, red, homozygous recessive. And then over here, it's no color, color. All right, so let's think about it. You could be red, you could be purple, or you could be neither, no color. So what is required for you to be red? You need little p, and you need to be little I, all right? So 1/4 times 1/4 is 1/16. Purple, you need to be this, which is a 3/4 chance, and you need to be little I, which is a 1/4 chance. So that's 3/16. Well, all probabilities have to add up to equal 1. So this is 4 out of 16, these two. So I automatically know that this is a 12/16 probability. Right? But if I wanted to do it just by solving the Punnett square, I think it's because I'm uploading the other video. My computer's slowing down. Well, look, the probability of no color is just 3/4. it doesn't matter what they are over here. If they get this 3/4, they're not going to have any color. So if I want to make the denominator a common denominator, I multiply by 4. Multiply by 4, 12/16, right? 12, 13, 14, 15, 16, 16 and a 16. All possible outcomes. All right, that's 13. Alkaptonuria, biochemical disorder. Dominant recessive. They don't tell us. Okay. I don't know. Oh, here it is. I can tell now. Right? It has to be. If you don't know, just make it up and see if it works. So you're like, I don't know. I'm going to make it dominant. I'm going to make it dominant. Okay. Well, if you're going to make it dominant, then Carla's got to have big A. Something. Right? She could be big A. She could be big A, little a. But she's got to have big A if you're going to make it dominant. Well, where's Carla getting the big A from? Anne's not affected. Michael's not affected. One of them has to have big A to give it to Carla, but they're not shaded in. It can't be dominant. It can't be dominant. It's got to be recessive. Let's assume it's autosomal recessive. I'm not even gonna try to figure out if it's sex-linked or not. I don't even think it's asking us to, right? But I don't know. Maybe in another video, I'll assume it's sex-linked, and then we'll see if it even works. Right? So George is big A, little a. Big A, little a, little a, little a, little a, little a, homozygous recessive. These have to be carriers to make a little a baby. And then Sandra, big A, don't know. These people are big A, little a, because they're getting little a from Tom. They must be getting big A from Sandra. So, big A, little a. Big A, I don't know. Big A, I don't know. Okay, I'll go back and see if sex-linked makes sense in another video. Okay, a man has 6, but it's autosomal. It's autosomal. A man has 6 fingers on each hand and 6 toes on each foot. His wife and their daughter have normal number of digits. Extra digits is dominant. Okay. So if the daughter has normal digits and that's recessive, and the mom has normal digits, so here's mom. Mom is little a, little a. Dad has to be big A, little a, right? Because if dad was big A, everyone has extra digits. You get an extra digit. You get an extra digit. Everybody gets an extra digit. But his daughter, they mated, and the daughter is little a. She has normal digits, so he has to be heterozygous. All right, imagine I'm a genetic counselor. Charles was married once before. He and his first wife had a child with cystic fibrosis. The brother of his current wife, Elaine, died of cystic fibrosis. Okay, the brother of his current wife died of cystic fibrosis. Charles and his first wife had a child who died of cystic fibrosis. What is the probability that Charles and Elaine will have a baby with cystic fibrosis? Neither Charles nor Elaine has cystic fibrosis. Right? This is basically the same question as the one that we did before. Right? So their child. Right? So these parents are carriers. These parents are carriers. So it's 1/9. Same problem as before, right? So unless I'm missing something here, right? So 2/3 chance that he's a carrier. No, whoa. I knew. Okay. Whoa. He's a carrier, okay? Because he's got a daughter that died of cystic fibrosis. But we don't know if she is a carrier. Right, so, okay, here it is. 2/3 chance that she's a carrier, right? Because I don't know if you didn't see in the last video with the other problem, like her parents are carriers, right? Her parents up here are carriers. So when carriers mate, you get these possible outcomes. But she doesn't have cystic fibrosis, so little a is not a possible outcome for her. So there's a 2 out of 3 chance that she's a carrier, and she would have to pass down little a. Over here, he's a carrier, but he still has to pass down little a. That's a 1/2 chance, right? So it's 1/2 times 2/3 times 1/2. So it's 2 over. Now I'm recording. Okay. I think I was unpaused after that explanation. This is 6 times 2 is 12, so it's 1/6. Okay. Black is dominant to white. A equals yellow band just below the tip of each hair in mice with black fur. Ooh, you have to have black fur to have the yellow tip. All right. This gives a frosted appearance known as a Goody. Expression of the recessive allele results in solid. Okay, so you got mice that are heterozygous. What is the expected phenotypic ratio, or phenotypic ratio? Okay. So again, this is just a deviation from the 9331 cross because you have like certain phenotypes showing up depending on the genotype. So let's see here. You could have all of these are going to be a Goody if the mouse has black fur, right? So that's the sort of thing that you have to keep in the back of your mind. So you can be black, no, a Goody, or I guess black solid. You can be black, a Goody, and then you can be white. And if you're white, there is no such thing as solid agouti. Like you're just solid white. It doesn't matter what you have for A, right? So what are the chances of this cross producing a black 3/4, no agouti 1/4? I believe it said agouti was dominant, right? Yeah. So that's 3/16. What are the chances of a black agouti? So black is 3/4, agouti is 3/4. So that's 9/16. And then just straight up white is 1/4, which is 4/16. 9, 13, 16. 16 out of 16. So this, I believe this 4/16 would normally be your 3/16, 1/16 in a 9331, but we're clumping that together. Because normally it would be like 1/16 recessive for both, and then 3/16 recessive for one and dominant for the other, right? But in this case, A doesn't matter. All that matters is that they're little b, because the agouti is irrelevant if they have white fur. Okay.